we're going to go ahead and get started. I don't know if anyone else will be joining us as we go, but if anybody's got any questions at any point, please feel free to get my attention somehow. I think there may be a raise your hand button or unmute or something. Whatever works for you. Today we're here to talk about capacitive braking. We're going to start with a general overview of VFD braking in as a whole. We're going to compare capacitive braking versus more traditional resistive braking and line regenerative braking. And we'll talk about the different pre-charge concerns that each of these the capacitive braking has, and two different ways of addressing them. And then we'll go over a few more details of each one. In general, a VFD stops a motor by taking the rotational energy of its load and converting it back into electrical energy. That's really what a VFD, what a motor is. It's a transducer. It takes electrical energy and converts it to mechanical energy, or takes mechanical and converts it back to electrical. And the VFD is just a means of controlling that conversion. One of the issues with a VFD is that, in general, they are unidirectional devices. They pull power off the AC line, but most of them can't put power back on the AC line. So when energy gets pulled out of the motor, it has to go somewhere, and the only place it can go is into the DC bus capacitance inside the drive. Capacitors, being physical devices, they obey certain laws, one of which is E equals 1/2 CV squared. As your voltage goes up, as your energy goes up, your voltage goes up. So as the VFD is braking the load, it's pulling energy out of the load, and that causes the DC bus voltage inside the capacitors, inside the drive capacitors, to elevate. As with most things, if the voltage gets high enough, something's going to break. So, not break, B-R-A-K-E, but break, B-R-E-A-K, like no longer function and catch fire. So, if the voltage is getting high enough to cause any substantial, be a risk of damage to the drive will fault. It'll stop running, and then you now have an uncontrolled load, which, depending on your circumstances, can be a serious problem. And in most cases is not particularly good, no matter what it is. So to keep the drive from faulting, that energy's got to go somewhere outside the drive. There are three fundamental ways of accomplishing that. One of them is the traditional resistive braking. You just take the energy out of the DC bus and shove it into a resistor, turn it into heat. That's most drives, or at least, I don't know about most, a substantial number of drives have a 7th IGBT inside them to control that braking. So if the bus voltage gets high enough that you're not at a fault level, but you're approaching it, the transistor turns on, and then at a lower level it turns off. So you just get this bang-bang hysteresis effect, burning off energy as heat. You can use a line regenerative approach or a common DC bus approach, which are kind of the same principle. You take the energy out of the drive and you move it to some other load that consumes it at that same time. Line regenerative just takes the energy, puts it back on the AC line where it gets consumed by something else. Common DC bus just skips the AC line step and just feeds the energy straight to a second drive by the DC bus connections. Either way, it's the same basic concept. Common DC bus is, of course, much simpler to implement. This third solution we're talking about today is capacitive braking. Rather than moving the energy from where it is to another location and using it at that instant, capacitive braking stores the energy from the braking event and uses it later at another time. In the same place, but at a different time. We do this by adding capacitance to the DC bus. The DC bus of drive has some finite capacitance in it, usually in the thousands of microfarads. How much voltage elevation you get is directly proportional, it's not directly proportional, but it is proportional to the amount of energy you're trying to store. If you add more capacitance to the bus, then for the same amount of energy, you get less voltage elevation. So if we can add enough capacitance to absorb the entire braking event, we don't need any other braking solution, in principle. In practice, you might want one anyway, but we'll talk about that later. This is particularly applicable for cyclic applications. So the classic one for this is a pump jack. In a pump jack, you motor for, say, 5 seconds, and then you regen for 5 seconds, and you motor for 5 seconds, and you regen for 5 seconds, all day, every day. Your regen energy with a capacitive solution can be captured and then just reused again during the next motoring cycle, which means that the only energy you ever pull off the line are the losses in the system. If your system is perfectly balanced, that can be very, very small. Now, you can do a line regen. Capacitive braking has similar benefits to line regen, but there are some cases where you can't use a line regen. If you've got a remote installation where there's not enough local load to consume what you're regenerating, then the utility might not like you shoving power back onto the grid. There are line regens that you can put power directly back on the grid, and there are line regens where you can't. The ones that are grid tied are typically much more expensive and not usually used for VFD braking. They're more for like solar applications. If you got a single phase installation, most line regens in the world will not handle single phase. Our Bonitron's 3545 product line will handle single phase at about 5 horsepower, but that's the only one in the world I'm aware of that will do single phase. And line regens don't work if your power feed is intermittent. If you've got even an intra-cycle outage or dip, your line regen might trip, and now you don't have any braking. So all of these problems are handled by capacitive braking. Since capacitive braking is completely it is not line interactive at all, any issues that a line regen might have because of the AC line are mitigated. This table compares our 4 basic options for braking and their advantages and disadvantages. Your standard resistor and transistor has an extremely low initial investment, or a very low initial investment, but its energy efficiency is literally 0. You are purposefully converting all the energy into heat. Installation footprint could be really small or extremely large, like larger than the rest of your drive cabinet, depending on what you're doing. And you have to cool your resistor, which can really increase your installation and investment costs and running costs. Common DC bus costs you almost nothing, is 100% energy efficient, extremely small footprint, but it only works in very limited applications. Line regen has the issues we've talked about. Costs a little bit more than a transistor and resistor usually does. Very energy efficient, very small footprint. Capacitive regen, by comparison to those others, the initial investment is probably higher than any of the others braking solutions. It's got a pretty big footprint, but it is, by comparison to some things, it's still smaller than most very big braking resistors. But for certain applications, the payback is excellent. In general, what this is being compared against, if you have a capacitive regen, what you're usually competing against is a resistor transistor solution. If you can use a line regen, that's probably going to be a better solution than a capacitive regen. There may be cases where that's not the case, but in general, a line regen would be recommended if it can be used. If it can't, then you should consider capacitive. One of the concerns with this approach is that drives can't just accept an arbitrarily large capacitance being thrown onto their DC bus. A given drive is only able to pre-charge the capacitance that's in that drive. There's some manufacturers will tell you that there is actually an additional capacitance limit that they can handle, and that's, if they tell you that they're within spec, that's fine. Others don't publish that spec. So, but in general, for any substantial amount of additional capacitance, the drive's not going to be able to handle it. For example, a smallish, let me make up a number here, 10 horsepower drive at 480 volt is probably only going to have something like 470 microfarads of capacitance in it. For applications, we're talking about adding several 100,000 microfarads of capacitance, or more. we could be in the farads potentially. So for those applications, there's just very little way that the drive's precharge is going to be able to handle that. Drive precharges typically come in two flavors. For smaller drives, it's usually an internal resistor with a contactor around it. In that case, if you try to put too much capacitance on that, there's a good chance you'll just destroy that resistor. It may actually catch fire, and now you won't have a precharge anymore. You need a new drive. So to make that not a problem, with the large capacitor banks we're talking about adding, you need an external precharge of some kind. There's two ways of doing that, and we'll talk about both of them in just a moment. There's another concern. If you have a large bank of capacitors in the hundreds of thousands of microfarads or in the farads, you may have safety concerns where if somebody needs to perform maintenance of some kind, a large capacitor bank might take hours to self-discharge. There may be safety standards in place that require the caps to discharge faster. We've seen some standards where if you remove power from the cabinet, the caps have to discharge to 50 volts within 60 seconds. So there's got to be some way of addressing that. And a third concern is that you may still want a resistive brake as a backup in some cases. If you do, you need to take that into account in the calculations we'll talk about in a few minutes. Now, the capacitors we're talking about, like I say, we could be talking about hundreds of thousands of microfarads. We could be talking about farads. There's dozens or hundreds of possible capacitors to choose from. Pretty much trial and error is the best way of figuring out what the most cost-effective combination is. We've developed some in-house tools that let us make lots of errors very quickly. So we can quickly identify what the most cost-effective combination for a particular application is. If you've got a cyclical braking application and you want to know what parts are involved to size the capacitor bank, we need these data points. We need to know the braking energy, because that's really what it all comes down to. We need to know, there are two ways of figuring that. You can know the horsepower and the time. If you have a 5 horsepower drive, it's not going to be able to do more than it's not going to be able to brake faster than its power rating. Usually it's got some sort of overload rating, so maybe 6 or 7 horsepower. But whatever the braking horsepower rating is and the time involved, that can tell you the energy. Another approach is if you know, sometimes we've been given braking currents. If you know the currents and the voltage, you can figure out the power. Power times time is energy, same as horsepower and time. You need the braking energy. You also need the nominal DC bus voltage. If you've got a 460 volt AC system, your DC bus voltage is 650 DC. If you're just sitting there not braking, 480 volt would be 680 DC. It's whatever your AC line is multiplied by the square root of 2. Now, if you've got a fluctuating AC line, you need to take into account the highest that line could ever be. So if your 460 could get up to 480 sometimes, you need to assume that it's 480 all the time to size your system correctly. You also need to know your maximum acceptable DC bus voltage. That's a point somewhere below where the drive is going to trip on overvoltage. That span is what determines how much capacitance you need to store the energy you're talking about. So if you want to store 1 kilojoule and you've got between 680 and 800 volts to do that, then that 1/2 CV squared equation tells you how much capacitance you need to store that much energy with that voltage span. One of the issues that I was talking about is if you've got a braking transistor, that braking set point is going to be lower, and you don't want the braking transistor turning on every braking cycle, presumably. So if you're willing to let the bus voltage get up to 800 and your set trip point's at 810, which is typical, you can do a lot less. You can do with a lot less capacitance than if you have to keep the voltage to below 750. That you go from 680 to 800, well, that's a 120 volt span. But if you go from 680 to 750, that's only a 70 volt span, and you get a squared effect as well on the voltage. So it's it's a pretty substantial difference. The more voltage play you've got to work with, the better, the less capacitance you need to keep the voltage down. And of course, the more capacitance you need, the more it costs. And the other issue that you have to take into account is the maximum precharge time. If you're putting a 1 farad capacitor bank on the DC bus, whatever precharge you're using is going to take some substantial number of seconds to bring that up to voltage. And when I say substantial, you could be talking on a scale of minutes. Now that's only going to happen at system power on. But there's going to be some number that you can put on how long your customer is willing to wait before the system's actually operational and capable of braking. If it takes 20 minutes to precharge, then that's probably not acceptable. 5 minutes might be acceptable, but really what it comes down to is current, right? The amount of charge stored in a capacitance is capacitance times voltage. So if you're trying to bring 1 farad up to 680 volts, then that's 680 coulombs. Well, if you're trying to charge that at 10 amps, that's 68 seconds to charge it. If you're trying to charge it at 100 amps, that's 6.8 seconds. So and that's assuming you have a constant current precharge, which you may not. But the principle is, the faster you want it precharged, the more the precharger is going to cost. So there's a trade-off there as well. All right, so to sum up this slide, if you have an application for which capacitive braking is appropriate, if we get Bonitron these 4 pieces of data: the braking energy, which you get either of these 2 ways, the nominal DC bus voltage, the maximum acceptable DC bus voltage, and the maximum acceptable precharge time, we can put those in our calculators and figure out what combination of capacitors and other equipment makes the most sense. There's 2 ways of precharging, like I mentioned. The one we've been advertising for a while now is the M3800. You use this circuit down here to precharge the caps. So during precharge, these DC bus contacts, these DC bus contacts are open during precharge. So you don't just slam a gigantic capacitor bank directly across, I'm drawing this DC breach contactor, sorry. You don't just slam a giant discharge capacitor bank directly across your drive bus. If you do that, you're going to either ruin your precharge or blow all your AC line fuses or damage your drive, or something bad will happen. So this contactor is open during precharge. This contactor is closed. So the giant capacitor bank is precharging through these external precharge resistors and this diode bridge and this set of contactors. The M3800 is monitoring all this. So when the voltage on either side of your output contactor is close to equal, these contacts, the AC line contacts, get opened and the DC contact closes. So now these capacitors are directly across the drive bus. The AC line contact opens because you don't want to have two rectifiers feeding the same DC bus. If that happens, then this small rectifier, this is only like a 20 amp rectifier, could end up trying to feed the entire drive, and it won't like that very much, and the drive rectifier may not care for it too much either. So the M3800 controller module, just a little DIN rail box, watches these voltages and makes sure that these contactors are only ever closed in a valid set of states. 3800 module does require an external 24 volt logic supply, but those are commonly available. We offer a wide range DC input supply called the 7001. We also offer a 7009 buffer module for a 24 volt rail, but 24 volt logic supplies are pretty readily available. You probably already have one in a cabinet somewhere. The other part of this system is this normally closed contactor that sits downstream of the precharge rectifier, but upstream of the resistors. If the system loses power for any reason, or the controller is instructed to, this contactor closes, these capacitors discharge through the same resistors they pre-charged through. So the system fails into a, if the system fails, it fails into a discharged safe state. Now, like I say, this is the system we've been advertising for a little while. We've sold a number of these. They work nicely. And there's nothing wrong with this approach at all. An alternate approach, though, that we've just been recently discussing is to use one of our M3713SC modules. 3713SC is a diode SCR rectifier. Takes three-phase AC input, puts out DC bus voltage, just rectifies the AC line. That's all it does. But it's got phasing. It's got SCR uppers, and it phases the DC bus voltage in slowly to prevent inrush currents from blowing your fuses. Very much like a lot of drive front ends do. We are offering a 3713 now with this NORL option. Normal 3713 SCs have a ramp limit option, have a ramp limit built into them, not an option. So if it tries to pre-charge for more than 5 seconds and fails, it stops to make sure it's not dumping energy into a short circuit. The NORL option does not have a ramp limit. So if you put a gigantic capacitor bank on the output of a 3713 SC with the NORL option, it will bring up the capacitor bank all the way, no matter how long it takes. And the amount of time it takes is limited and is determined entirely by the size of the capacitor bank and the size of the 3713 SC. We offer those in as small as, I believe the smallest is 30 amps, and we offer them as high as 375 amps. So that's probably going to be enough for any reasonable application here. The way this setup works, it's much simpler, obviously. There aren't all these contactors that you have to worry about switching things in and out to protect the drive front end. The drive front end simply is left disconnected. There's no AC feed to the drive in this case at all. The drive runs entirely off the DC output of the 3713. The capacitors are there all the time. Nothing ever switches in and out. So the drive front end can't be damaged because it's not doing anything. If you want to discharge this, we do offer a separate discharge kit instead of in this case, the discharge controls are integrated into the 3800 system. The discharge for this is a separate kit that we sell. Kit 3628T and M3628R. It's possible some of you are familiar with the M3628T that we've been offering for several years. Kit 3628T is a replacement for that that's just been released in the last month or so. Kit 3628T compared to M3628T is about half the price and much more capable. It can discharge any capacitor bank up to 1,000 volts DC. We could probably do up to 1,500 if you really need it with a little bit of work. And although if you've got a VFD bus at 1,500 volts DC, I'd like to know what you're doing. And we can discharge any size capacitor bank you're interested in. So this solution here, the 3800 solution, requires a bit more integration. There's many more discrete parts that have to be wired together. 3713 solution, fewer discrete parts to wire together. I believe they're cost comparable at the end of the day. Which one you end up using may depend on the vagaries of your specific situation. So both probably need to be considered in any specific installation. In general, the savings on a system like on a capacitive braking system are very comparable to the savings of a line regenerative solution. The capacitive solution will be marginally more efficient, but you can only save what you're losing, and line regens are typically 99% efficient. So there's not too much to be saved over a line regen. So you can use mostly the same calculations. If you want to know how much you're saving, figure out your braking energy per cycle, which again, horsepower and time. For example, if you had a 5 horsepower system braking for 5 seconds, that's about 19 kilojoules every cycle. Cycles per year, so if you have a 10-second cycle, so 5 seconds motoring, 5 seconds braking, that's about 3 million cycles a year. Figure out your cost of electricity, depending on where you are. It could be anywhere between 8 cents per kilowatt hour, and if you're on a generator, it could be much, much higher. Total savings per year can work out to $2,000, in this particular example, about $2,500. ROI on a system that did this, something like 4 years at the price of electricity. Other concerns for the for capacitive braking applications. One is that current distortion will get worse. The larger your cap bank is during motoring, the narrower your conduction window is. I wish I put a drawing in here illustrating this. The reason you get harmonic distortion of current from a rectifier is that the rectifier is only conducting at the peak of the wave. Whatever portion of the wave is your DC bus isn't flat. It's actually got this. It starts up at a peak that's charged to every cycle, and then droops off, and then gets recharged back up and droops off. The bigger your cap is, the smaller this droop gets to be, and the narrower your conduction window at the peaks are. So instead of having, so the more capacitance you put, the narrower and taller your current spikes look. So your current distortion, in absolute terms, gets much worse. The reactor helps some, but it's only about a 5 to 10% difference in my experience. However, depending on the application, your total demand distortion may actually get better, because if you were comparing against a resistive solution, you were having to pull all the current you needed every cycle. With a capacitor solution, every braking cycle, you're actually storing energy for reuse, so the total energy you're drawing off the line goes way down compared to a resistive solution. So the harmonic content of what you're pulling looks worse, but you're pulling so much less, it may not matter. Another interesting point is that the large cap banks you're throwing on the bus also add ride-through capability. Now, if all you want is a ride-through, there are probably more cost-effective ways of going about it than this, but it's an interesting additional selling feature. This 5 horsepower system here, that costs roughly $10,000 like I said, I just ran these numbers through a calculator pretty quickly. It costs about $10,000 for a 5 horsepower system to brake in these conditions. That additional amount of capacitance also added 4 seconds of outage ride-through. So if you've got a situation where you need braking and you need ride-through, this is worth considering, because you get both, whether you want it or not. Both of these solutions, the 3800 solution and the 3713 with no ramp limit, both of them are applicable to single-phase installations. We have not directly installed any in single-phase installations yet, but I think it just hasn't come up yet. Both of them are designed for 3-phase at present, but the amount of customization required to make them work single-phase is relatively small, so we're not too concerned about that. Another difference that's worth knowing, 3713 is UL listed and 3800 is not. So if you're concerned about UL, this little controller guy is not UL recognized. We could make it that, but we just haven't. It's designed to UL standards, it's just not UL. This 3713 is UL listed and in all frame sizes and all voltages. So that will not be a concern. Applications we've seen, pump jacks have been the primary application for capacitive braking we've seen so far. The way a pump jack works, there is constant cycling. You motor for 5 seconds and regen for 5 seconds if you're properly balanced, and the amount of energy involved is very cyclical. Whatever energy you're putting in, you're also pulling out, minus any loads, assuming the pump jack is properly balanced. Minus any losses. Pump jacks are also typically or often out in the middle of nowhere, so you can't regen and have that consumed by another local load. So line regen doesn't work very well in those cases. Other applications where we've considered capacitive braking to be good, stamping machines, very comparable application. Stamping machines are typically in a plant, so you don't have that out in the middle of nowhere advantage, but they are very cyclical, relatively constant isn't the word, relatively unchanging from cycle to cycle load. Another application we've seen is crane hoists. Cranes are their AC feed to the hoist is often questionable because the trolley is moving back and forth, and if you've got any problems with your brushes or shoes, AC line regen can have some issues. And a lot of cranes have been out there for a very long time, so they have some installation. They haven't necessarily been maintained in just the highest possible working order. So little problems like an intermittent contact that wouldn't necessarily bother a drive can screw up a line regen. So in conditions like that, a capacitive brake can be considered as well. All right, I think that's all I have to say at this moment. What questions does anybody have? I know that was a lot of information all at once. For whatever it's worth to anybody, we have typically we've used two kinds of capacitors for these applications that have most often proved cost effective, but we're always reevaluating. One of them is a bracket with about 10,000 microfarads at 900 volts on it. Just several of those in parallel, however many is appropriate. Another approach that we've used is to stack ultracapacitors, usually 160 volt, 5 or 6 farad modules in series to get up to a certain voltage, to get up to the necessary bus voltage. One issue you run into with that is granularity. If you have to stack at least 6 of those caps to get the voltage you need, then you will have at least a farad of capacitance no matter what you do if you're using ultracaps. So there's a very definite changeover from roughly 1/4 of a farad cost effective with electrolytics to 1 farad cost effective with ultracaps. There's not much in between. Right. Nobody's got any questions, comments, thoughts? All right then. Well, if anybody has any applications where you think this would be appropriate, or if you have any further questions or concerns, you all know where to find us. Please call us at any time, and we will be happy to talk to you more. Thanks for coming.